Welcome back again. So in the previous video, we discussed about the basic elements of the control systems, open loop system, closed loop system, and the basic whatever the practical real life examples or real life equipment what we already see. Okay, but mainly thing is how we can able to control means we can able to control a system in a mathematical model only, because the whatever the system will be there, the system is a physical system. Whatever the controller is also, it is a controller, but the controller will only understand like it as a, it is only understand a mathematical modeling based only. So that need to be identified. And in this lecture video, we are going to know about like what are how we can able to model a physical system in a mathematical based way. So in this total video, we are going to discuss about like it as a, what are the types of mathematical modeling we can able to do, and how a mechanical system is converted into electrical system only we will see with one basic example or two basic examples. Okay, so first of all, what is the basic mathematical modeling? This total mathematical modeling series will be in the two video parts, because one is will be discussing with the mechanical systems and another video will be discussing with the electrical systems. Okay, so then you can able to easily identify like it as a both mechanical systems and also both electrical systems, how easily you can able to mathematically you can design on your own self whatever the system it will be. So first of all, you need to know about like it as a what is the necessity to make a mathematical modeling system, because as I already said like it as a the system is a mechanical system which is driving through or controlled by electrical system, and the whatever the controller is, the controller only understand like it as a only zeros or ones or mathematical modeling only. That means it need to have a digital information need to be there. The digital information where it how it can be processed means it can be processed only through a controller or either through any of the other equipments. So the system, whatever the system will be there, the system is mathematically represented is on three different variations. So first one is based upon the differential equation. Second one is based upon the transfer function. Third one is based upon the state space equation. So it will, these three can able to identify any these three types we can able to make any system into mathematical, and it will help us to know how the whatever the physical system will be, the physical system how it is behaving, like whatever it is behaving it in a low voltage, whatever it is behaving in a high voltage, whatever it is happening in a sudden ups and downs, whatever it will be there, this optimization everything can control. We can able to simply, at least we can able to 50 to 60% we can able to easily identify like how the system can able to create or behave in different scenarios. So basic, we will take like a basic mechanical system which is having it, I call it as a one mass will be there, that is any of the one system. Let's take it as a one mass based one rock or something like that. We will take that as a mass, so representing inertia. And the damper means which is related to the friction or resistance, that means which is can able to holding the force will be there, the force is that one. And the spring, whatever the spring will be there, the spring is having the elastic force. So one is having a mass which is holding by a spring, and which is having a friction, that means it is simply friction means I can simply say it like it as a, it's a gravitational force whatever it is having. So this is how it will happen. So by the Newton's second law, which is a very famous one, that is F equal to ma. So we mathematical, before going into the next couple of videos, so you need to know about like it as a derivations, integrations, Laplace transforms, very much familiar. So you please go through these three things before going to the next couple of videos. Okay, so Newton's second law, as we already know, force equal to mass into acceleration. So that acceleration is we change it into in terms of the velocity. Here we taking as a velocity as a x velocity or a force it is delivering. Okay, so f equal to ma, that equal to m into d square x by dt square. So by these equations we can able to understand like it as a, how the motion of that system is operating. Okay, and next one is we will discuss within a simple example which is having a both damper, damper, spring, and also mass. Before the system, if you see here, sorry, if you see in the before slide, we all what we have is the damper is in the downside, but now we are having a damper is in the front side itself. So by this one, what we are having is we can have a equations like this one also. So m d square x that equal to ma, which is related to the mass f equal to ma, and this is related to the what are the damper, that is this one. So b into what are the velocity applied on this one, and the what is the spring constant will be the spring velocity also is applying this one. So whatever the force, total force is acting on this this side and equal to the upside. So that means what are the Newton's third law is the applied force equal to the what are the drawing force. In the same way it is the thing, that means equal to equal and opposite reaction, in the same way it will happen. So if we apply the whatever this equation is, this first equation, force equation, if we apply the Laplace transform, so then we will get the complete equation in a Laplace transform transfer function based equation itself. But before going to that one, we need to have some assumptions that like it as a, we need to take the initial conditions as a zero, then only we can able to understand like it as a from zero state onwards it is starting that one. So regarding that, so if you apply the Laplace transform for the d square x by dt square, we will get the thing called it as a s square into x of s. In the same way, dx by dt as a x s into x of s and x as x of s. And the t time function, this is the total time function will be there. The time function is converted into s domain. Okay. So if from here what I am transferring is I am taking the right hand side, sorry, left hand side to x of s by f of s. So thus, then what will happen is this is completely a force based output equation in a transfer function. So this is one basic example for this mechanical function to a mathematical modeling. So if you see, this is a mechanical system, but here whatever we are getting, it is a completely a mathematical function which can able to give a total output whatever we are able to understand in that way. And the next one is about we can see like it as a mechanical rotation system also. For example, mechanical rotation system means the pulleys will be there wherever in the olden days we are getting the water things will be there. So in the same way, there are multiple way of rotating elements will be there. So that those are linked with the mechanical system. Those type of systems are called the mechanically rotational systems. So if you see here, so what are all the forces? There are mechanical and electrical say, analogy. Analogy means terminologies. We can simply say it like this. So always you need to remember like it is. In mechanical, if it is force means, then here in electrically it will be as a voltage. In the same way, in mechanical it will be saying it as a velocity. In electrical it will be like it as a current. In mechanical it is like it is a mass means, then in electrical it will be considered as a inductance, and the damper is considered as a resistance, and the spring is considered as the inverse of capacitance. So this analogy will always be able to understand like it as a how a mechanical system can be able to equally convert to the electrical system, because till now before now whatever you did is we can understood like it as a one physical system. That physical system can be a mechanical system or an electrical system or whatever it will be. So from this whatever analogy is there, this analogy is completely will be able to know about in the next couple of videos. After that, this one itself we can able to understand the, how exactly a system can able to deliver and how a system can able to transfer the total all mechanical parameters into electrical parameters. So we, according to this one itself. So this exhibits the equal analogy. So how wherever where we all we utilize this one means so this complete transfer function based modeling or what are the state space modeling or what are mathematical modeling we will use in the automotive suspension systems and robotics. Robotic arms, if you see the robotic arms moving here and there, right? So that can be controlled by this one. And also vibration analysis means it is not in a completely, you don't know, you don't see in this one. So it will be in a very research side based things. So by this, whatever happen is we can get to know wherever it need to be effectively be controlled or wherever it need to be effectively not be able to control, and wherever it need to have a lead and lag compensator PID. So PID means proportional inversional differential controller based things will be there, and lead lag compensators will be there. So how effectively we can able to control a mechanical system or a electrical system or a physical system, whatever it will be, we can get to know by this mathematical modeling. In the next video, we will see the like it as a now the electrical system is derived based upon a transfer function. Okay, till now we are not derived the electrical system. We designed only the physical system and also a mechanical rotational system analogy we discussed. But now next in the next video we will see about how an electrical system can be mathematically transferred into based upon a transfer function. Okay, thank you.